ordinary least square estimator. So we will use our same ordinary least square estimator, OLS estimation. So we will choose a random sample again because we cannot find the population regression model. So we will use a sample, and then using the sample we will find out the regression model. So that's why we have all hat, and here the beta 0, beta 1, beta 2, this will be the population population regression coefficient. This is the estimate because we using sample, right? So you can calculate the residual, also residual. Real population regression also will have a error term, but since we're using the sample, so this is a sample error term, is you observe the real one minus estimated y. Actually, this is the same, and estimated y is, this is the y, estimated y equals is beta 0 plus beta 1 x1, right? Of course, this is all estimate, plus beta 2 x2 plus right? And then we trying to minimize this summation of the squared error, right? And then estimate to minimize, and we decide this beta 0 hat, beta 1 hat, and so on. So the same logic we have seen in the simple regression. Only difference is just we have a multiple parameters. And it's not beta 0 and beta 1. We have a beta 2, 3, 4, 5. Interpretation of multiple regression models, I already explained what the beta j means. Is how much does the dependent variable change if the j's independent variable is increased by 1 unit. But here the condition is holding all other independent variable constant. So this is the kind of the ceteris paribus. This is the kind of actually this is a Latin, but use a lot in economics. We analyze. So this is the holding. Actually, this ceteris paribus means is if we hold everything else fixed, and then we are changing only one variable at a time. So we wanna, when we usually do this kind of analysis, is we wanna find out what is the effect of a certain variable. So I don't wanna other thing change. So we're gonna fix all other things and then change the one variable. Then we can observe the our result will change by only changing one variable. So this Latin phrase means is what if we hold everything else constant, and then if I change only one variable at a time. So that's why this is the kind of problem if two factors has a correlation. We will talk about that later about the model selection. This is a GPA at college can be determined this 1.29 plus 0.453, and high school GPA plus 0.0094 times. This is the achievement test score. This is with the SAT, right? SAT is more famous, but both of them are like a college entrance exam at US. So ACT is one of the exam, like a SAT. So what does this number means? It's a 0.453. So if the high school GPA is 1 point higher, everything is same. So there's two students, one student, these two students has exactly same ACT score, but one student has a 1 point higher than the other student in high school GPA. Then what will be the college GPA? The student who has a 1 point higher in a high school GPA will get a college GPA higher by 0.453. Okay, that's what this 0.53 means. But this magnitude does not tell you how the strength of the impact, because the GPA is what is the GPA range is maybe like a 0 to 4.5, right? However, the ACT score is like a 30, 40, like a 10 times greater scale. That's why this number getting smaller. Yeah, if the ACT score is like a SAT, just like a SAT score, SAT score is like about the maximum score is 1,600. So when you multiply 1,600, you have to multiply very small number, right? So this small number, if it doesn't have a very strong effect, it will have a small number, but also depends on the scale of the factor. If the scale of factor is bigger, then this coefficient will be smaller. So we cannot directly compare, okay, this is a 0.453 and this is 0.0094. High school GPA is more important than the exam score. Maybe, but we cannot tell by looking at this coefficient, because the 0.0094 is because of the scale of the test score. So we have to, yeah, that will be the little different story. So we cannot tell which one is more important here. Maybe the high school GPA is more important, but I don't know. And properties of the OLS on any sample of the data. Fitted value, yeah, I already write down this one. So this is the fitted value, we call the fitted value, or estimate predicted value will be using this formula, because this is our estimate of beta 0, beta 1, and so on. And residual will be calculated by this one, and we already seen the formula, right? Residual. This is the residual calculation, and then I already write down here. And what we can expect is we already seen this as the all summation of the residual should be 0, because you may have a positive residual, you may have a negative residual, but if you add up, that should be 0. If it's not, the average of the residual is not 0, then you have to modify your model. Actually, your model is not correctly regressed. If your regression was correct, then this should be 0. And multiply x with this residual should be 0 means this residual should not be correlated with any factor. Right? If the residual is affected by the factor, but again, I think I already explained in the simple regression, your regression was wrong. You have to update the coefficient of the factor, because you didn't capture all the effect. So if you want to see the residual is a real residual, that should not be affected by your factor. So that's why the covariance between the factor and the residual should be 0. That they should not have a relationship. And of course, if you put the all, everything is the mean, then you should be able to see the dependent variable means. Partialing out is there's a two different way to find the coefficient, and then you can the first one is regress the variable on all other. No, this is the partialing out method. Okay. So you can just simply do the regression and then you can find the coefficient, but this way you can find the coefficient also. So I will explain. Let's say our y has a beta 0 plus beta 1 x1 plus beta 2 x2, right? And then plus u. And then think about it. If you want to find out beta 1, maybe, yeah, then you have to, you can just regress and then you find out beta 1. But how can you do is you can just regress with your specific variable that you are interested in, and then do some other regression. Let's say it's gamma 0 plus gamma 1 x2. So your variable, do the regression of your variable on all other variable. Okay, and then you find out this gamma, and then there's a residual, right? So you collected all the residual, and then what you can do is you can do the regression is y equals something a0 plus a1 and this u. So you put it here. So what does it mean in the meaning here is if I take a u here, what is this u means? This u means all x1 value except x2 effect. What do I mean is if you can calculate the regression here, if x1 is a sum, not completely but partially can be explained by x2, some part of x1 can be explained by x2, right? And some part is not explained by x2. So u is only the part of x1 that is not explained by x2, right? And then if I using this one to estimate y, then this alpha, the a1 should be same as a beta 1. Which means if we do the regression with all the variables together, this beta 1 is only the x1 effect, excluding the x1 part that can be explained by the other variable. That's why we call it a partialing out. We can take it out of the all other partial part that can be explained by the other variable. You're just taking out. So I will show you